you, Nancy. So I know that it's after lunch, so hopefully this isn't going to be too boring. It might be hard. And so if you have...
Before you start going, you need to put on your microphone.
Ah, that's right. I have forgotten about that. This. Is that, no. No, the other way. That's it? Is that okay? Yeah?
I think so.
Okay.
It's on?
Can you hear? No.
No, it's
Right? How do you turn it on? On. There we go. So now, it's okay? Okay, sorry about that. So, okay, so yeah, please interrupt me at any time if you have questions or at the end. And so, as Nancy mentioned, we're going to talk about confidence intervals. So, this is the outline for today. Where did this go? No, this is a different one. So we're going to start with an example, then just a reminder of how do we answer research questions. If you were in the morning, some of these things might be repeated. Sorry about that. But we're going to see then how to report. Then some definitions. This is not working anymore. Oh, yeah. Just is very, very light, so it might not be useful. Okay. And again, examples, and talk about clinical importance and some misinterpretations of confidence intervals. So, this example, MS, background, and some of the things are exactly from the paper where it's coming from, right? So, people living with MS require complex care management, and the treatment, these therapies, is the current pharmacological standard of care. So understanding DMT use and healthcare utilization by different geographical areas among people with multiple sclerosis may identify potential gaps in care and can be used to inform policies and individual practice. So if you can see here, the aim is to inform policies and practices. So supposedly it's very practical, right? So we want to see if there's a difference in different parts of an area. So objectives, and this is how they have it, is measure DMT use in healthcare utilization among people living with MS. And they separate in urban and rural residents and also in zones, right? And so they have those two things. And this was published in 2025, a year ago, so not long ago. So going back to how do we answer a research question? So we search the literature for information, or if there's already theory. And what's our population under study? Then we got data, either we collected or we see if the data are available. And so then can we get data from the whole population under study? As we saw this morning, usually we can't get get information from the whole population. So then we get a sample, right? And the idea of the sample is that represents a population that we want to measure, this. And this is what we're going to be talking about. Then we analyze the data. So we summarize information from the population. This is when we have a sample. And then we describe the sample and make inference to the population, like we saw this morning. And we draw conclusions. And some of the conclusions can be changing policy, as we saw in this case, that was the aim of the study. So again, going back to the MS example, so if the data were collected appropriately, we're going to assume that. Again, reminder, these are the objectives of the study, right? See if there are differences in rural and urban areas and also in different zones. And this is a place in Canada, in Alberta. And so they talk about statistical analysis, what they did, and that's important in publication. You always have to present that. Now, I'm not going to be talking about if the analysis were correct or not. That's a different thing. I'm just going to be talking about how they conclude things. That's the main thing when we use confidence intervals. Which, yeah, I have issues with the analysis, but that's a different talk. So the results that they present are just your typical table 1, right? That it says that we have an overall, well, the sample are N, or sample size, and percentages, and then the urban, rural, and all the different zones that we want to compare. And this is just percentages, descriptives, and I'm just showing that the sample size large for each of the, right? So they don't have issues with sample size. Now, the results as presented, they just have a 1.2-fold higher proportion of those living in urban areas receive a DMT compared to those living in rural areas, right? So they just present 32.3 versus 27.4. And that's it. That's the only thing that they present. And then the healthcare zones, when they have the Calgary, Edmonton, and the other areas. Oops, what happened here? Technical issues. Okay, sorry about that. They just see that they have in Calgary 32.1, Edmonton 32.8, and the others 29.6. And then they just mentioned who received was significantly higher, and that's it, and the proportions. So if you see this information, you start to think, is it enough or not, right? So here is the table 2, when they have this. They talk about 32.1, 32.8, and then the 32.2, all these different proportions, and they just see, if you have here, they have just sort of a asterisk and whatever, and they have a footnote where they describe what that means, the A, the B, and the asterisk, and so on, right? And here they say, well, we're going to see more detail later, but they just say here, A, B, well, here's asterisk, significantly different between urban and rural, and then A, B, and C, significantly different between the geographical health zones. Yep, that's the only thing that they present. So we have to go back to how to report. Is this the correct way of reporting or not? So from the New England Journal of Medicine Statistical Reporting Guidelines, we have, and I'm going to mention a few of them, not all of them, but general requirements recommend authors draw a clear distinction between statistically significant and clinical significance. So far, we're just checking results. We haven't seen discussions. I'm going to talk about also discussions, because sometimes in discussion is where you argue about the clinically importance and if it's significant or not clinically. Then significant tests should be accompanied by effect estimates with standard errors or confidence intervals. So when you start reading those things, start to think of the example that we had, did they present that or not, right? In general, p-values larger than 0.01 should be reported to 2 decimal places, and then 3 decimals in other cases, and if it's less than 0.001, just p less than 0.001. Did they present that? We haven't seen that either, right? So, and the thing is that this paper was a year ago, and these recommendations were longer, like long time ago, right? Longer than that. So we have to think of, okay, some definitions. Some of you might know already these definitions, but I'm just going to go through them. And these are extracted from some of the papers. So informally, a p-value is the probability under a specified statistical model that a statistical summary of the data would be equal to or more extreme. Yeah, so maybe that's the definition that you've seen out there. Or a p-value for a comparison of 2 groups is the probability of observing a result at least as extreme as the observed result if in truth there's no difference between the groups. So basically what all this says is how likely it is that what we observe happens under what we assume. And this is what we call we assume is what we call sometimes the null hypothesis, right? So under what we assume, how likely is it that we observe what's going to happen? And both definitions talk about more extreme. So what does it mean that if we observe something, but it also is far away from other points, that means that something beyond that point also is going to be less likely to be part of that null hypothesis, right? And usually we compare p-value with a significance level alpha, which we saw also today in the morning, right? The alpha, the probability of type 1 error. Yeah. And conclusions are usually made if there's an effect when p-value is less than alpha, right? And that alpha is the statistical significance, and usually we use a 0.05 for that. Yep. Questions? Nothing? Okay. Then, clinically significant. The clinical significance is practical importance of a treatment effect, right? So we saw statistically significant, now we're going to talk about clinical significance. So it's just the practical importance. Also, we have what it is, an effect estimate or effect size, which we saw a little bit in the morning. So it's a point estimate. What is a point estimate? So a single numerical value, so for example, a mean, a sample mean, and it's the best approximation for the population value. And we hope to be close to the population value, but usually it's not going to be exactly the same as the population value. If we have different samples, then we get different point estimates. Now, so we have variability. Now, so going back to the definition of effect estimate, is the magnitude of difference between two groups. So we're comparing two groups. Let's say we want to know what the difference is between mean 1 and mean treatment A, mean treatment B. So that the effect estimate is the difference in the means. So mean difference, risk difference, relative risk, odds ratios, etc. Now we have what is the standard error. Basically, it's a measure of precision of the estimate, and it shouldn't be confused with the standard deviation of the data, right? They're different things. One can be used to calculate the other, but they're not exactly the same. So then we have what it is a confidence interval. It's a way to quantify uncertainty in our guess of the population parameter. Can be taken as a range of plausible values for the population parameter based on the sample. So we have the sample. From the sample, we calculate the confidence interval. So it's a range of possible values for our parameter. We don't know what our parameter value is, but this is good. That's why it's a range of plausible values. Usually we have a 95% confidence interval. And what it is that if we collected many samples, let's say 100 samples with in similar conditions, the same sample size and so on, we expect 95% of those samples to cover the true population parameter. Again, we don't know the true population parameter, but we expect to have that 95% to cover them. So a definition that it's in this publication is it's a range of values either side of the estimate between which we can be 95% sure that the true value lies. P-value and confidence interval. There is a close relationship between p-value and confidence interval. So confidence level, it's that we saw usually 95%, and it's the 1 minus alpha, the alpha that we saw from the significance level. Right? So they're very, so if you have an alpha of 0.05, then your confidence interval is going to be a 95% confidence interval. And we compared the alpha is the one that we compared with the p-value as we saw before. So the p-value by itself tells us nothing about the size of the difference. It's just a probability, and it says nothing about the difference. And so they're not that informative per se, right? So confidence intervals should be used because they indicate the strength of evidence about quantities of direct interest, such as treatment benefits. So confidence intervals give extra information. P-value is just the probability of observing something. If we have the null hypothesis, confidence interval gives more information regarding the measure of effect, the treatment benefit. So now that we have all these definitions, that's what we saw, what is recommended, we go back to the MS example. Did the example follow any of the recommendations that we saw? So again, going back to the recommendations in how p-value should be reported, right? 2 decimals, 3 decimals, or less than 0.001. We see this, and we only have, again, the A, B, asterisk, and so on, and footnotes. They just mention other things, but here they just, as I mentioned, they just say they're significantly different. That's it. Right? There's nothing about exact p-values. There's nothing about less than 0.001. What if it was a p-value of 0.051 or 0.049, which were very close to the 0.05, but they just dichotomized it, so it did not giving a lot of information, right? Again, should be accompanied by effect estimates with standard error or confidence intervals. Going back, they just report the table. They have a 1.2-fold higher proportion, and they just mentioned the 3.2 versus the 20.47. Do they report an effect estimate? No, because they don't do any difference between the proportions or ratio, anything, right? So they don't report those. So just by seeing those two numbers separate, yeah, we can just calculate the 1.2, but it's not giving us information. They're not reporting it with confidence intervals. So we're not seeing the whole picture, right? And even this one is even worse because they just have the Calgary, Edmonton, and the health zone separate proportions. They don't have effect estimates between any of them, no confidence interval. They just said significant, and that's it. So we don't have p-values, we don't have confidence intervals, we don't have effect estimates, we don't have anything. And this was just last year where supposedly these recommendations have existed for a long time and they haven't done it. So that's the thing that they're still, it was peer-reviewed publishing, so that's, in a way, it's a shame because it passed peer-reviewed, but it's not ideal, right, how they're reporting. So they report only one effect size and no confidence intervals. Then that authors draw a clear distinction between statistical significance and clinical significance. Again, the 1.24 increase, and then the proportions for each one. So again, maybe in discussions, they talk about some of this clinical, if it's clinically significant. So there is this thing about discussion, and they don't talk about clinical significance or anything. Right? So that's a long thing. I'm not going to read it, but if you see that they don't mention anything about, is it important in practice? Does it mean that, yeah, the resources we have to change from one area to the other, or just provide more resources in one area? It doesn't say anything, right? So again, no discussion of clinical significance, not magnitude difference. So at the end, it's no measure of uncertainty, no clinical or practical significance at all, right? So they're not following the recommendations. So then, another example, diabetes. Determine whether circulating, I don't know what that is, SDC 163, is different in those with diabetes, with any traditional complications versus diabetes without traditional complications. So that's another example. And what they do is they just say that it's a 1.3-fold higher in D plus group. They present the value. I assume that it's a confidence interval. They don't mention, and they don't say if it's a 95% or what type of, what level. And then they mention the D minus, and then also the value with the confidence interval, right? But this was not statistically significant, 0.08. Okay, this is giving us more information. But are they giving us the whole information? So they don't do the effect size. They don't present us a difference. We can do the 282.7 minus 224.9, but the confidence interval, we cannot calculate the confidence interval with those values, right? We need more because we need the standard error in order to do that, and it's not that straightforward just adding and subtracting the separate confidence intervals. So also they report 1.3-fold, but we're talking about differences. We're talking about continuous. So it would be better to have the 282 minus the 224 instead of one over the other, the ratio. So I'm just going to have this hypothetical example, and they're hypothetical because I couldn't find anything over there in the literature, but to have an idea of why it's important to have the clinical the significance versus the statistical significance. I talk about both. So to evaluate if SBP changes in patients following a treatment. So let's say that we have 68 patients, and then we have a pre-post, and we measure the SBP pre the treatment and then post-treatment, and we saw that the difference was 2.5 with a 95% confidence interval of 1 to 4 with a p-value of 0.0014. Now, looking at these values, what can you conclude or what can you say about these values? So, is this statistically significant? It is, right? Because our p-value is less than 0.05 if we use a 0.05 cutoff, right? So yeah, we can say that it changed. What does the confidence interval say? So the range of possible values for the true population parameter could go from 1 to 4 with 95% confidence. So it's a 1 and a 4, a clinically like significant change in SBP. Well, maybe if you're dying, if your SBP is really high, maybe like reducing it by 1 or by 4, it makes a difference. But usually SBP reducing by 1 or 4 or changing it, not really affecting, right? So clinical significant, is it really? So that's a part of, okay, it's statistically significant because it gave you a p-value less than 0.05, but is it really, really important? Like, would you change a treatment, or would you encourage this a treatment based on these results? Not necessarily, right? It depends. But so just basing it on statistically significant is not enough. You have to see the values. You have to see if you're going to spend money in this treatment just to increase or reduce whatever you want to do between 1 and 4, right? Questions? Now, another example. To assess if patients taking a medicine have a higher heart rate compared to patients not taking the medicine. So we have the mean difference between the two groups is 15 beats per minute with a 95% confidence interval between 0.1 and 30, right? And we get the p-value is not significant. Here, I'm not reporting the but it's not significant. Based on this information, what would you say? Would you put money on this treatment? Would you suggest this treatment? So, it is statistically significant? No, right? At a 0.05? No, because we have, well, p-value is not significant, and our confidence interval also covers 0, so then it's not statistically significant. The confidence interval says that the range of possible values can go from negative 0.1 to 30, right? So let's say that what you want to do is, I don't know, the treatment is for another thing, and I don't know, and at the end you're measuring if the if the heart rate is changing. So would you give the treatment to the patients? Do you want your patients to have a heart rate as high, can be as high as 30, or negative 0.1? What would you do? Anyone? Would you say that heart rate, it's okay, like doesn't matter heart rate because it was not statistically significant? The thing is that clinically significant, if it goes as low as 0.1, as high as 30, if that treatment is going to increase the heart rate by 30, that can be bad, right? There's a chance that it can be, because your statistically significant said, no, it doesn't matter. This doesn't increase, like we don't have evidence that there's a change. It's well, not that change because we're not doing change, but it's different, right? The heart rate. But if it can go as high as 30, it might be bad. So you also have to think about, okay, yeah, negative 0.1, the negative 1 doesn't affect, it's not a big thing, but the 30 can be bad. So you have to pay attention also to the values in the confidence interval. If you just go with 15 beats per minute, also that's a little high, you have to think. But if it can go all the way up to 30, that's even worse, right? So you also have to see the two values, the two limits of your confidence interval. So that's why confidence interval gives you extra information, right? Because it can go as high as 30, and it should also be included as part of p-value, your estimates, and so on. Yeah? So conclusions based on clinical, we don't have enough evidence to conclude that BPM changes. So then you say, okay, yeah, go ahead. If it's based on statistical significance, you can say, doesn't matter, give the treatment, not a problem. But if it's based on clinical significance, you have to think more of, right? Would you have the treatment? Right? Okay, so clinical importance may be suggested when the results are statistically significant and the estimated treatment effect exceeds some specified amount. The combination of point estimate and confidence interval provides information to assess the clinical importance of a treatment, as we just saw in the previous examples. A stricter criterion is that the whole confidence interval should show benefit greater than specified minimum. And if we're evaluating a treatment that decreases the risk of an event, but well, we have to determine what is the benefits, and then we have to see what the values are of our confidence interval in order to see if it's of clinical importance or not, or if it's going to harm our patients or things like that, right? And well, we have past seminars, Meaningful Difference. You can, if you're interested, you can see those two seminars that we have in Stat Central to talk more about the meaningful difference. Now, we have also the concept of credible interval. I'm just going to mention the difference. I'm not going to cover this because that's a different thing. That's different seminar, would be a different seminar. So a confidence interval is what we have in frequentist statistics. So it's a frequentist interval. So the parameters are fixed. So we have a parameter, a population out there, a mean out there. We don't know, but that's fixed because that's a population is fixed and cannot be random. The interval, so the limits, the upper and lower, are the ones that are random. And the interpretation interval is one of the possible intervals that contains the parameter. And it's not the probability of the two parameters in the interval. And then we have what it is, a credible interval, which is Bayesian interval. That's a different type of statistics. We have Bayesian statistics. And here the parameters are random, and they follow a prior distribution. And the interpretation is the probability the parameter lies in some fixed interval. So confidence interval, the interval is random, parameter is fixed. Credible interval, the parameter is random, and the interval is fixed. And I'm having these two definitions, or these two intervals, because people get confused with the definition. They confuse one with the other. Now, common misinterpretation of confidence intervals. And well, before this, any questions? How much time do I have? Okay, still okay, right, with time. So, common misinterpretation. The specific 95% confidence interval presented by a study has a 95% chance of containing the true effect size. So that's an interpretation, of course, the title says, but it's a no. Reported confidence interval is a range between two numbers. The frequency with which an observed interval contains the true effect is either 100 or it's 0. Right? If it includes or it doesn't include. Refers only to how often 95% confidence intervals computed from very many studies. In this case, I have in italics, but I wouldn't mention the word studies here. I would put samples instead of studies. Would contain the true size if all the assumptions used to compute the intervals were correct. It is possible to compute an interval and can be interpreted as having 95% probability, and this is what we have as Bayesian interval that we saw just. But that's what I had the two definitions because, again, people get confused with one and the other, which are different. An effect size outside the 95% confidence interval has been refuted or excluded by the data. That's also a misinterpretation. Why? Because we have, when we do tests and we have calculated confidence intervals, yeah, we have to follow assumptions from the model because we need a model in order to compute the test and the confidence intervals. But not only that, we also need assumptions regarding the design of the study, the population that is correct. So we have so many assumptions behind there. So that's why we cannot say, no, it's not correct, or the value outside is impossible. No, because we have to meet several assumptions in order to do that. So we cannot conclude that it's refuted or excluded by the data. And this is what I mentioned, right? Combination of the data with the assumptions and the 95% criterion that needed to declare that effect size is outside of the interval. And we need stronger conditions because we need to prove, again, that our experiment was done correctly, that all the assumptions regarding the design are perfect, also that assumptions of our model are perfect, and so on. And that doesn't happen all the time, rarely. Basically, all of the assumptions being met is not that common. If two confidence intervals overlap, the difference between the two estimates or studies is not significant. That's not true either. It's up to the degree of how they overlap. but just by seeing them separate, you cannot conclude that. So that's why you should always calculate the difference between the two treatments, for example. May overlap substantially, and yes, the test for difference between them may still produce a p-value of less than 0.05. If the two fail to overlap, then using the same assumptions used to compute, we will find that the p is less than 0.05 for the difference. So if they don't overlap, yeah, you can say with that more surely they're going to be different. And if one of the intervals contain the point estimate from the other group, we will find that the p-value is also greater than 0.05. So just because they overlap is not, you cannot conclude many things. It's better to do the difference or the effect estimate, the confidence interval. The confidence interval for the difference is not the difference of the limits of the confidence intervals. Okay, so just by looking at the confidence interval separate, you cannot calculate the confidence interval of the difference. Another misinterpretation, an observed 95% confidence interval predicts that 95% of the estimates from future studies will fall inside the observed interval. That one I've never heard in practice. That was in a publication, which is, I think, it's all to the extreme. I don't know, this is all the way to the extreme. So under the model, 95% is the frequency with which other unobserved intervals will contain the true effect. So many of these refutations are from previous ones. They're applied in several misconceptions. An observed interval either contains or does not contain, and only to how often the 95% confidence intervals will include the true parameter. Another one, if one 95% confidence interval includes the null value and another excludes that value, the interval excluding the null is the more precise one. Also, I've never heard that one, but that's also really weird. And no, of course, that's not correct, right? Because it doesn't mean anything that one includes or not the other, right? It's more of the precision that we're interested in. So it's not a matter of including or not excluding. I think that's more of a cherry picking what I want to hear and just keeping the one that you like. Okay, questions? So remarks. One journal now bans all statistical tests and mathematical related procedures such as confidence intervals. Because since people have used a lot the p-values, just making decisions of significant, not significant without taking into account clinical significance or just dichotomizing like, yes, it works, it doesn't work. So now many journals have banned, and I think that's bad because you're losing also a lot of information if you ban, right? So some might argue 95% confidence intervals also force a 0.05 level cutoff. So the example that I had before of the minus 0.1 to 30, and it was 50, yeah, people might say 0 is in there, so yeah, I'm also can conclude that it's not significant, right, using the confidence interval. So the idea is not to show the confidence interval, but not make the same conclusion as, yeah, 0 is there, so it's not significant. The idea is to see, as we talked about, that it can go from negative 0.1 to 30, or to, yeah, it was to 30, and what are the implications of those two values, right, the extreme and all the possible values in between. So, well, because it's lumping together all the effect sizes, so it's similar to dichotomizing p-values, as I mentioned. But other argues that it gives more information because then you can get better, like, conclude in a better way if you have the confidence interval and not, and either with p-values or confidence interval, you shouldn't say, yeah, reject, not reject. You shouldn't say it's significant, not significant. You should say, well, yeah, the values can go from here to here, so you as a clinician or someone make a decision of is it worth using that treatment, or is it going to damage, or is it right? Because also it varies. It depends on what the implications are for those things. So sound practice in the interpretation of confidence intervals include discussing both the upper and lower limits, as we saw in the examples. Do they have different practical implications? Not only whether it contains the null hypothesis, as I mentioned, and confidence interval is an estimate subject to error. So we have to think also that it's Also, a realization is a one sample out of several samples that we can do. It's subject to error. It provides a rough indication of uncertainty, giving all the assumptions. So also, we have several assumptions, the model and the design. So also, we have to be careful on how we talk about it, and does not rule out values outside the interval. Indicate the strength of evidence about quantities of direct interest, such as treatment benefit. Thus, they are particularly relevant to practitioners of evidence-based medicine and help avoid misinterpretation. So again, people are pushing off, yeah, you should also, include your confidence intervals. Limitations: reflect only uncertainty arising from sampling variation, not additional uncertainty due to failure to follow the protocol, non-random loss to follow up, and so on. So we don't have, again, like if the design that we have is wrong or is bad, it's not reflect confidence. It's going to be reflected in the confidence interval, in the results, but we don't have a way to measure it, right? In a way, everything that we've done already is going to give us a result, but we cannot say, well, this confidence interval is wrong because our design was wrong or our method was wrong, whatever, but we have to think of that confidence interval came from many assumptions, came from many things, so it still has limitations. In most studies, it's often the case that a confidence interval includes both no treatment effect and substantial treatment effect. So the authors are advised to not comment on the non-statistical significance. And as we saw, again, with the example, the negative 0.1 to the 30 had the not treatment, add up to 30, had everything. So just saying significant, not significant is not valid. Just mention what the implications of the two limits are. And as some authors argue that the use of words like significance and confidence shouldn't be used, right? So they argue of concordance intervals, like a lot of people, and also even other use of p-values and so on, because saying significant, not significant, there's strong words, and then people confuse with correct, not correct, or just say, they use the dichotomization and they shouldn't be done. So again, compatibility and things like that, right? Compatibility intervals. Among the many reasons, most scientific settings, the arbitrary classification, not significant, is unnecessary. Yeah. Estimation of effect sizes will have more important, basically all it is saying calculate confidence intervals, right? Not only the p-value. And switch from reliance on statistical or practical to criterion. So what we have to do is we should what I've been talking all throughout is, again, check for the p-value and also check for the confidence interval, see if it's going to be effective. What do you think about your treatment? Would you recommend your treatment to someone? Would you put your money on something, right, based on the confidence intervals? And basically for practical recommendations. And that's it for my talk. So hopefully it was useful.